Okay, hi everyone. What I want to do here is to illustrate how you would use change wing and tail rigging angles in order to achieve a particular trim and angle of attack setup for an aircraft. So here we are with our twin turboprop geometry, and we want to set the wing and tail rigging angles to achieve these conditions: an overall coefficient of lift of 0.37. The aircraft wants to be in trim, so the pitching moment, or about the center of gravity, that CMY, should be 0, and we want the overall angle of attack for the aircraft to be 0 degrees at that coefficient of lift, so that the fuselage is aligned with the oncoming flow direction. So firstly, to note here is I've already set up the center of gravity for the aircraft because I computed the neutral point and set the center of gravity according to the static margin. So this is where all the moments are going to be computed around. That's compared to the origin for the aircraft is actually set at the center line of the wing leading edge. So this is 0.855 meters behind the center line, the leading edge of the aircraft. So I'm going to be playing around with the wing and tail rigging angles. So firstly, let's have a look at the wing. The way to do this is, if I want to transform the whole wing, let's say I want to put it at 45, that's a bit extreme. Let's maybe make that 25 degrees angle of attack, or 20 degrees. You see that I'm rotating the whole wing by changing this angle. So first we're going to start off with both the wing and the horizontal tail set to be 0 degrees angle of attack with respect to the aircraft. We're going to use VSP aero. So now under advanced, we want to turn off stability calculation. We're just doing a regular load distribution. Again, I'm using the vortex lattice method. I've set the wing reference area, span, and chord according to preliminary calculations. And I've got the alpha. I'm going to choose 5 angles of attack to do my load distribution sweep from -2 degrees to +2 degrees. And let's launch the solver and watch what happens. So we're going to be seeing the load distributions coming up. First for the top for the wing and on the bottom for the tail, and you'll see that the tail is basically lifting down. We're looking for an average coefficient of lift of around 0.37, so somewhere around the middle here. It's going to be somewhere around the center of these 5 computations. So we'll plot a sweep and we'll plot up coefficient of lift versus angle of attack. And you see that I'm reasonably close here. For an angle of attack of 0 degrees, I've got a coefficient of lift of about 0.33. So I need to change the wing rigging angle a little bit to raise it to a more positive angle of attack. And in fact, it turns out you can compute this approximately, but I've done a bit of playing around and I found that 1/2 degree is pretty good. So I've just changed the wing rigging angle to a slightly more positive value than the original one, and I'll go ahead and do the solution again for the load distribution on the wing and tail. So you just have to wait for these 5 to go through. You need around 5 points. You can get away with 3 probably, but 5 is pretty good. Okay, now plot a sweep, and again we're plotting coefficient of lift versus angle of attack, and you'll see at 0 degrees angle of attack I'm pretty close to my required value overall coefficient of lift at 0.37. So that's good, but now I need to see, is the aircraft in trim? So I now need to plot CMY, the moment coefficient around the center of gravity, and you'll see that in fact the aircraft is trying to pitch nose up with the horizontal tail at 0 degrees angle of attack, because at coefficient of lift of 0.37 I've got a positive value of pitching moment is 0.025, so it's trying to pitch nose up. That means I need to add some down elevator, or in other words pitch the leading edge of the whole tail surface up, and I'll first try doing that by 1 degree. So let's just confirm, let's put in 10, and you see that's pitched the whole, that's like down elevator. So I want to do it just 1 degree, I know that's in the ballpark. And I'll go ahead and launch my solver again. Every time you change these settings, a new default degenerate geometry file is automatically regenerated to run the solution. You see I've got a moderately high, but not outrageously high panelling distribution for the wing and tail. I probably should reasonably do a convergence check on these results by increasing the panelling density, but it's okay for our current purposes. So we're going to again go ahead and plot a sweep. We're going to plot coefficient of lift versus CMY, and we'll now see that at a coefficient of lift of around 0.37, we've got a nose down pitching moment of around minus 0.038, something like that. So we've added too much down elevator, and in fact it turns out a angle of attack of around 0.4 degrees is pretty good. You can find these things pretty much by linear interpolation, because these computations are all essentially linear. Go ahead and launch the solver again. See that these load distributions are more like triangular than elliptical, at least at low angles of attack. They're going more and more elliptical, and hence the span efficiency factor will be going up as we increase the angle of attack. And again, plot our sweep, coefficient of lift versus CMY, and you'll see that our coefficient of lift of 0.37 right here is giving us a pitching moment of pretty close to 0, so that's in pretty good state of trim right there. And now what we need to do is go back and check an overall aircraft angle of attack. It's going to be pretty close because we didn't change the tail rigging angle very much, and in fact it's pretty good now. It maybe just the wingers that are slightly high to high angle of attack, but it's really not by much. So at a coefficient of lift of 0.37, in fact, at angle of attack of 0 degrees, in fact, gives us a coefficient of lift that's a little bit higher than 0.037, but it's good enough, really, from the point of view of doing this. That's reasonable. 0.1 of a degree variation is pretty hard to. You're pretty close at that. So let's just say that we've finished our rigging setup, and now we've got both the correct center of gravity to give us a static margin requirement, and we've got the wing and tail angle set to bring the aircraft into trim at a desired coefficient of lift. That's it.